name is Leonard Kleinrock. I'm chairman of the Computer Science Department at UCLA. We have here a really exciting and dynamic environment. One of the activities that contributes to that environment and that excitement is the constant flow of visitors who come and spend time with us and interact with our faculty and student body. Each year, we select a few from among the very best researchers in the field and ask them to participate in our Distinguished Lecture Series. The high point of their visit is the presentation of a lecture to our faculty and student body. And at that lecture, they present the state of the art in their field of specialty. They describe the research results, the open problems, and the directions in which the field is likely to go. And as you might expect, these lectures always generate a great deal of enthusiasm and interaction. I'm really pleased you've chosen to join us today. Let's go inside. The lecture's about to begin.
Welcome to the fourth of our distinguished lecturers. Once again, the cookies are gone, so it's time to start. Today I have a really great honor to introduce to you someone I've known for more than half my life. Now, that may not mean much in terms of how old you are. When you figure how old I am, that's a very long time. Longer than most of you are old. Ivan is one of the smartest guys I know. He's made some enormous contributions. And as I go through his biography, you'll see exactly what they are and why I think so much of him. So let's go back to the early days. His dad was born in Dunedin, New Zealand. His dad wanted to build dams. In New Zealand, you could build about one dam. Okay? So he came to the USA in the 1930s, to the Snake River area, and built a lot of dams in Idaho. His dad got his PhD in London after fighting in World War I. His mother was born in the early 1900s and was of that generation of young women who were eligible to marry the men who went to fight in World War I and didn't come back. There were just no men around. It was a really hard time. In fact, as Ivan points out, World War I was the first war where more people were killed by bullets and shells than died by disease. It used to be that the healthiest army won. In World War I, the tide turned, and the most mechanized armies won. So, and his mother got a master's degree in Edinburgh, for example. So he was destined to become something wonderful. And in particular, he became an engineer. He has an older brother, Bert, and the two of them were paired off for a long time, up until today, as you'll see. If they wanted any electronic parts or technical education, there was no constraint on what they could get. Movie money, toy money, something else. Education, science, readily available. He was raised in Scarsdale. His father commuted 2 hours each way, each day, into New York. You think a 15-minute commute here is bad. And that was without freeways. Both Ivan and his brother Bert were interested in electronics from early on. They both studied ham radios. Bert is still a ham radio operator. Ivan is not. Bert taught Ivan all about AM modulation long before Ivan could do trigonometry, so Bert taught him trigonometry as well. In fact, Bert taught him quite a bit of his mathematics background. When Ivan went to take his license for the FCC, he went to New York to the FCC to get his ham operator's license. He went to take the first class exam, which is the highest you can get. And the examiner said, "No, you little kid, start with the third class exam." So he took that. A few minutes later, passed that. Took the second class exam. A few minutes later, passed the first class exam. Typical bureaucracy in New York, but an example of Ivan's capability at the 9th grade. He learned the Morse code, of course. If you're going to be a ham operator, you have to be very proficient in Morse code. They had a key and a sounder in the hallway in their home. The mailman came in one day, saw this device, and started pounding away. And so Ivan and Bert were thrilled, and the mailman who had been a key operator in World War II offered to teach them. So every afternoon, for about half an hour, the mailman would come, spend a half hour in the house teaching them, and leave. Now the neighbors wondered what was going on inside that house. Every day the mailman was coming by. And as Ivan puts it, his mother was willing to sacrifice anything, including her reputation, for their education. Ivan went to school in Scarsdale as high school. He took science electives, and his mother pushed them both to take physics, and he took it as a freshman. Bert, brilliant fella, high achiever, they meet up again at MIT later, got 99 on the New York Regents exam out of 100 in math and science, and Ivan beat him. Constant source of grief or competition to Bert. And the reason that Ivan could do better than Bert, because Ivan had Bert to teach him as well as the school system. Bert only had the school system. He got the advantage of both. In high school, two things happened. His mother introduced these boys to Edmund C. Berkeley. He's the one who named the ACM the ACM. And in fact, Ivan began to work for Berkeley for a while. Now, Berkeley had a computer called Simon. This was a very powerful computer. It had all of 6 words of memory. 6 words. Length of the word, 2 bits. So it didn't have a very sophisticated programming language. It was called punching binary onto paper tape. And Ivan wrote the only program on that machine, and he taught it to divide. Now, he could take any number up to 15 and divide it by any number up to 3. Now, divide a number by, and he did it by cases. Divide by 1 is easy. You can just repeat the number. Divide by 2, shift right. Divide by 3 was a problem. It took 90% of the code. He worked it out. Double precision arithmetic. His father was an engineer, as I said, a very good engineer, a civil engineer. But he always appreciated the value of knowing mathematics and the mathematics underpinnings of the things he was building. Ivan appreciated that as well. And that combination is part of the success story that Ivan continues. Because in 9th grade, his mother took him to see a gentleman by the name of Claude Shannon. Small name I hope all of you know about. Shannon also, his great talent was combining math and physical field and engineering. At the visit, both Bert and Ivan were there. And Shannon told Ivan the story much later when he went to graduate school, that these 2 kids came to visit him, and the older brother did all the talking. Except at the end of the day, Ivan asked one very penetrating question, and Shannon remembered that for years and years later until Ivan came back to work for Shannon at MIT. In fact, when he went to MIT and worked for Shannon on his PhD, we'll get to the details later, Shannon only graduated 3 students, Ivan Sutherland, Bert Sutherland, and a fellow named Henry Ernst. And Henry Ernst was one of my office mates at MIT. And Henry built a mechanical hand. And he could make it do little robotics things. This is the early 60s. And I remember after Henry left, his desk was empty, the telephone rang one day. And I picked it up. It was a local newspaper. They wanted to talk to this fellow who made the mechanical man. I said, no, it's a mechanical hand. They said, what's the difference? Already back then, they were playing their game. Ivan went to Carnegie Mellon University and had full tuition. He got a Westinghouse scholarship. And he remembers 2 particular professors there. I'm trying to give you the feeling for where the background comes from that brought Ivan to where he is. 2 key professors there. One of them named Leo Finzi, who taught him magnetics. Remember magnetics? And a fellow named Arthur Milne, who's still alive. He's emeritus right now. And he basically had a laboratory there in which they studied the behavior of transistors back in those early days. And the important thing is that Ivan would get his hands on transistors, the early germanium transistors, and play with them and experiment with them. And recently, when Ivan went back to Carnegie Mellon to give a distinguished lecture, he had the great honor of honoring that professor. It was a wonderful reunion at the time. Ivan graduated first in electrical engineering from Carnegie Mellon. He got married in Pittsburgh just after graduation and took his wife Marcia as far away from her mother as he could. He was accepted at MIT and chose not to go there, rather he went to Caltech, further away. Okay? He had worked for IBM in his senior year and really got interested in computers, that plus the Simon experiments. Now, while he was at Caltech, after getting his master's after 1 year, Marvin Minsky and Oliver Selfridge came by and said, MIT has much better computer education and capability than Caltech. So why don't you come? They talked about the TX0, the first transistorized computer, and the PDP-1. So Ivan went. He reapplied to MIT after he had turned them down the year before. He had an NSF scholarship, so they reluctantly accepted him after really courting him the first time. Once he turned them down, MIT did its thing, accepted him. Ivan came by, and I remember when Ivan first appeared, having had his master's degree in his hand. I earned my master's degree there, and we sort of got together at a point in our careers when we both had to take this thing called the qualifying exam at MIT, which allows you into the doctoral program. This is not a qualifying exam. It's a killer exam. It's an extermination exam. Okay? The idea is to get you out instead of in. Of all of us who took the exam, and there were some really smart people taking them, some of them who have lectured here, Ivan, who came in from Caltech without having gone through the MIT curriculum, scored top in that exam. That was the first time I noticed him. Okay? He came in and scored top from no place. Interesting guy. What did he do for his dissertation? He did
Caltech ain't no place.
small place. His dissertation was on a Sketchpad, a wonderful graphical capability for designing structures with a very advanced computer at the time, which is a very weak computer in today's measures. There were three notable things that Ivan did with that system. First of all, it was the first object-oriented program ever written. He dealt with graphics objects as we talk about them today. The second thing he did was a wonderful man-machine interface, basically dealing with rubber band structures, local gravities, mechanically oriented things. And the third thing was that he would put constraints on the structures he was drawing and ask them to satisfy certain constraints, like these two lines should be parallel, and this line should be at 45 degrees here with this line, and maybe right angles with this one. Unrealizable constraints. And the system had to fuss around and try to satisfy those constraints. Well, many of you should know about Sketchpad. It's a wonderful graphic design system which anticipated many of the things we do today. And I remember when Ivan took his thesis defense. In fact, he, I, and Larry Roberts all took a piece of our defense together at Lincoln Laboratory because we all use the same computer. And Minsky was there, Shannon was there, a few others were there. And Ivan explained how to create these structures and let the system satisfy these constraints. And then he got to talking to Shannon. And the machine was behind Ivan. And Minsky, I don't know if you know the story, Ivan, Minsky wandered over behind him and started creating a structure and pushed the constraint button, satisfy constraints. And he created a real wild structure. And the system didn't settle down. It was like the Sorcerer's Apprentice. These circles were growing, and these lines were appearing on the screen. And never said, and Ivan had no idea. He was looking at Shannon. This thing was going on behind him like a wild, wild system. He left MIT, had to do his Army service, had been with the ROTC. He was sent to NSA. NSA measures how many computers they have by the number of acres of computers that they have. Bob Sproul's father stole him from NSA and brought him to ARPA. Ivan was the second director of the Information Processing Techniques Office at ARPA. And in fact, one of the things he tried to do was start a networking program here about 4 years before the ARPANET began. And the interesting thing is it didn't take. There were some administrative, bureaucratic problems. Across the campus, different departments and colleges and schools couldn't get together to network 3 IBM 7094s we had here at that time. It's still going on. Still going on. The predecessor at that office, Licklider, had the following comment. He said, the approach was to gather the best people in the country and ask them what the appropriate thing to study was, and then let them do it. That's not quite the philosophy today, but there's still some elements of that around. He went to Harvard with tenure in 1966, right out of the box, and it took him a year to figure out what tenure is. Tenure means freedom. In this case, academic freedom. Years later, when a company he started went public, he found out another form of tenure, tenure for life, freedom from economic worries. Freedom is the name of the game, and I've told you that before. You want to get yourself in a position where you can do what it is you want to do. So in fact, while at Harvard, Bob Sproul was an undergraduate student. They invented virtual reality. They had the first head-mounted display. They could see things. When you turned around, you would notice more things that you hadn't noticed before. They had to solve the 3D clipper problem, which then was the basis for a company that he and Dave Evans started called Evans and Sutherland. Now, there was Dave Evans from Utah and Ivan from the East Coast. Where should the company be? Well, the answer was Evans had 7 kids, Ivan had 2, so the answer was Utah. And Ivan learned more about Mormons and what a hard time they had in the West, or what kinds of capabilities they have than I think he ever wanted to know, but he certainly learned a lot about them. After that, 6 years at Ivan Sutherland, came back to Santa Monica, bought a lovely house, which he still owns. He was there last night. Took a position at Rand. Then Caltech offered him a job. And he did a little thing like take a man named Carver Mead, package him, and present it to the public, and basically make VLSI an academic subject, a kind of capability that led to Moses or Moses, as Ivan pronounces it, a kind of capability for doing VLSI chip design and fabrication. Ivan is the youngest person ever to be elected to the National Academy of Engineering. He's also a member of the National Academy of Sciences. Received the Turing Award in 1988. He's currently a Sun Fellow, as it says up there. But his biggest joy in life is to work for his brother at Sun. So they still are working together. Let me tell you what he feels is the message for you young people. The choice of projects that have been easy enough to do, but far enough ahead that they've been significant, are the things he likes to work on. Sketchpad, head-mounted display, VLSI. His advice to you is pick something you can do well. The world is full of easy problems. Don't bang your head on the hard ones. There's plenty of good, easy ones around. The trick is to go and do it. Ivan, please.
Well, we could fill this time with stories about the good old days, but I think the good old days are more exciting for the good old fellas than for the young people. I'd like to talk about some of the work that I'm currently engaged in. I've been interested over a long period of time in asynchronous computers. The idea being, instead of making every part of the machine wait for the next tick of the clock, to let each part of the machine proceed at its own pace, with the hope that the ensemble of equipment will thereby be most rapidly able to complete its overall job. Now, whether or not one can actually do that is still a matter of some question. I'm quite good friends with a man named Gordon Bell, who for many years was the chief engineer at DEC. And Gordon is quite an outspoken person. He has many opinions. Some of them I agree with, some of them I don't agree with, but I like the man very much. His opinion on asynchronous computers was expressed one day when he said to me, Ivan, he said, are you pouring your effort down the asynchronous rat hole? And the answer is yes, I'm pouring my effort in that direction, but what we don't know is whether or not it's a rat hole. So you will notice the final caveat on my list here. It says these ideas have yet to be tested and may not, in fact, be any good. So I'm going to tell you some things about what we're doing in the hope that you'll find them interesting and without any definite knowledge that they are, in fact, the right direction to go. I'm going to talk about a thing that I call the Sproul pipeline processor, which Bob Sproul actually invented. The story is quite interesting. I went to Boston in 1992 for the summer to work with Bob. Bob is also a Sun Fellow and works in our Boston office. And I decided I'd spend the summer there. I arrived on the Tuesday right after the Memorial Day weekend. And he said, I think we might try building a machine about like this, and laid it out on the blackboard. Now I know on Friday he didn't have that design because I talked to him on Friday. And what he says is, threatened with my arrival, he figured he better have something to say. So the more we've looked at this design, the better we've liked it. It's kind of an interesting design, and I'm going to tell you quite a bit about it today. So here's a little outline of, oh, by the way, he calls it something other than the Sproul pipeline processor. And I call it the Sproul pipeline processor, and I will prevail ultimately. Okay, so here's the lecture outline. I'm going to talk about the architectural idea, talk about instructions and results, describe a single stage of this pipeline processor. We're going to talk about the state diagram and what the problems of dealing with it in an asynchronous way are, where the register file fits the arithmetic, and so on. So I show this so you know what's coming, and then I put it out here so I can see what I'm supposed to talk about, and don't get too distracted. Now, the intent of the spiral pipeline processor is to make a machine that is, number one, buildable as an asynchronous device, and number two, rather simple and repetitive in its design. So the intent is that there be a series of stages, each of which is very alike to the other stages, and each of which talks only to its immediate neighbors. Now, most computers, in fact, are built as pipeline processors, but there is generally a rich interconnect between one stage and stages 2 or 3 stages away in the pipeline in order to speed the transmission of information from one part of the pipeline to another. It's very difficult to do that in an asynchronous system because anytime you send information from one place to another, the two places have to agree on when the information is to be sent and when it's to be received. And so if you're sending information every which way, it kind of prevents all of those senders and receivers from operating on their own. So an important feature of Spiral's design is that each stage communicates only with its neighbor. Now, people orient pipelines in their discussions in different ways. I like to orient the Spiral pipeline so that instructions flow up through the pipeline. And I do that so that if you take a snapshot of the instructions in the pipe, it looks just like a program listing. Older instructions are above and new instructions are below. And I think that puts less stress on my brain in thinking about it than other orientations. Naturally, the electrons in the transistors don't care whether they're right side up or upside down, but my gray matter does. So here is a typical, now don't believe in particular the stages I've described here, but here's a typical arrangement of a spiral pipeline processor. There's some kind of an instruction fetch unit at the bottom, which fetches instructions and stuffs them into a pipe going up. And they get processed in various stages. There's a decode stage somewhere there, which figures out whether they need some source information, and if so, requests it from a register file at the top. And the instructions proceed up, maybe to an index adder or a multiplier stage up here somewhere. When an instruction reaches a stage that can execute it, it stops, and it waits until it has all the information that it needs to execute. And I'll tell you how it gets that information, but when it has all the information it needs, it then executes and has some answers. And it does two things with the answers. One thing it does with the answers is to carry them forward with it to the top of the pipe where those answers get recorded in the register file. And the other thing it does is to drop the answers into the results pipe, which is the downward flowing stream of information, in case any following instructions might be interested in those values. And sure enough, a following instruction might be interested in those values. For example, here's a set of dummy instructions. It's not a very interesting program, it's just a set of instructions. So A gets B plus C and so on. And the value of A for this instruction obviously is the value that was computed there. But the value of A for this instruction is not the one that was computed here, but rather the one that was computed here. So when this instruction executed, it dropped that value of A into the results pipe. And this instruction, seeing that value in the results pipe, said, okay, that's the value I want. But what was it that kept this instruction from getting that same value? Well, one of the rules of Spiral's architecture is that if a result meets an instruction that is going to recompute the value, namely this one, then the old value must be destroyed, later on to be replaced by the new value. So that's kind of the idea. It's a very simple architectural structure in which instructions flow up and results flow down, and you can imagine, I think, quite easily how such a thing could in fact be computed. Let's look in one stage of a spiral pipeline processor and see what's in there. Well, obviously there's an instruction register and a result register. Now these are quite long registers. The instruction register for a Spark processor, for example, contains the operation code. It contains the names, that is the addresses, of the source values. And it contains the source values themselves. So if there are 3 source values, which there are in Spark often, that's 3 32-bit quantities or more than 100 bits of source information. And there will be some resultant, some destination information as well. So there's some 200 or 250 odd bits in each of these stages. But hey, it's only transistors, and in 1995 transistors are incredibly inexpensive and incredibly small, so we can afford to have a lot of them. Let's look inside those registers and see what the parts are. So here's an example where we have an instruction that has 2 sources and a destination value. And there's a result has two values in it here, let's say. The gray areas are intended to represent the names of those values. So if this is an instruction that's supposed to add register 5 to register 7, this gray area will say 5, and this will be the value that's in register 5. This will be 7, and this will be the value that's in register 7. If those values are known. If those values aren't known, a bit will say, I don't know that value yet. And when this ultimately computes, this will be the name of the register that that answer is supposed to go into, and this will be the answer value. Now, how do these values get filled in? Well, when an instruction meets a result in some particular stage, that result might be carrying a value for register 5 that this instruction needs. And so the instruction copies that value, copies the value from the result into the source position, and then carries that value forward with it. We call that process garnering. We say that the instruction garners the values that it needs from the results pipe. Now, we've only recently had a name for the process that takes information from the instruction value and affects the result. The corresponding process to affect the results pipe we call RenRag, which is just garner spelled backwards. And the RenRag process has sort of 2 parts. One is when an instruction computes, the value that the answer that it gets needs to be put into the result pipe. And if a result meets an instruction that has already recomputed that value, so here's a result carrying a value that it thinks is the value for register 5, and it meets another instruction that says, I've computed a value for register 5 and my value is 17, obviously the result coming from above must be from an older instruction. And so the RenRag process says, if a result meets an instruction that has already recomputed a value, the result should pick up the new value. So that's the opposite of garner. Garner is to take the value, RenRag is to put, okay? If the result meets an instruction that hasn't yet computed, but is going to compute a value, then the result value has got to be marked as invalid. It's got to be eliminated so that subsequent instructions won't see it. Well, if you think about this for a little while, you'll notice that results in the results pipe exist only between one instruction and the next instruction that computes that value. And the result of that is that instructions in between can only see the proper answers for the values that they need. And it's that basis that says the semantics of the Sproul pipeline, in fact, leads to correct execution of the computer program. Now, what does all this have to do with asynchrony? Well, since each stage is talking only to the stages above and below, we can pass the instructions up the stages as fast as the stages are willing to accept them, and we can pass the results down as fast as the results are willing, as fast as those stages are willing to accept the results, and everything can proceed at its own merry pace. Nothing in Sproul's semantics says that instructions have to execute in order going up the pipe. In fact, a later instruction further down in the pipe, if it has all the values that it needs, can execute before one further up in the pipe. And so, out-of-order execution, a thing which can speed the overall processing, is perfectly possible. Supposing, for example, that you're doing some kind of a dot product loop, you have some indexing operations to be done. Those indexing operations might proceed 2 or 3 trips around the loop ahead of the actual hard arithmetic that's doing the dot product. And so out-of-order execution is something that Sproul's architecture gives you for free. Now, if all of this is going on, willy-nilly at its own pace, and everything's happening, whenever it wants to, there's one very serious problem. Supposing an instruction is going up and a result is coming down, and it just so happens that they're about to meet when they both decide to move at once, and the instruction never gets the opportunity to see that result. That would create major chaos. So the one thing that the asynchronous design has to be sure to do is to be sure that every instruction meets and can garner from every result going the other way down the pipe. Okay? So what do you have to do to ensure that that's true? Well, this was a puzzle for us the first 6 or 8 months of this project. And Charlie Molnar, who's another chap that was around MIT at the same time I was, been a friend of mine for half of my life, as has Len, worked with us a bit on this, and he came up with what we call the Molnar 5-state diagram. It's quite a simple diagram, but it's a little subtle. A stage can be in any one of 5 states. It can be empty, it can have an instruction only, a result only. It can be full and not yet garner and renrag, or it can be full and have done the garner and renrag process, and those are the 5 states. The important thing is that if there's an instruction only, the stage has a choice. It can either pass that instruction up to the next stage, or it can accept a result from above. But it must not do both, because if it did both, then the instruction and the result would have passed. And similarly, if a stage has only a result, and there's an instruction just below, the stage can either accept the instruction or pass the result, but not both, because to do both would cause it to miss. And so in those 2 cases, arbitration is required to decide whether or not the stage will accept the next instruction or pass the result, so that both are not done. Now, there's a whole other lecture I can give about arbitration, which is one of the tricky problems in asynchronous design. It's actually pretty easy to do, but you have to understand that it's necessary and where it's necessary. We spent a fair amount of time worrying about how many arbitrations must there be in each stage. For a while, I was in favor of 2. Charlie Molnar was in favor of 1. He prevailed, thank heavens. And so the design that we have actually looks like this. Between each pair of stages, we put what we call a cop, which is basically a traffic cop. And what the cop does is the arbitration that's required to decide whether the instruction below shall be allowed to move up or the result above shall be allowed to move down, but not both. And so there's basically the design of what we call a counterflow pipeline, a pipeline in which there are 2 asynchronous paths, one going in one direction up in this case, the other going in the other direction, and enough equipment to ensure that every element going up meets with and can interact with every element going down. Saw that slide before. Now let me talk about the register file. The register file in this design goes at the top end, the far end of the pipeline. I gave this lecture at Stanford 6 months or so ago, and I got to this part. I said the register file goes at the far end, at the last part of the pipeline. John Hennessy was in the back of the audience. He couldn't resist. He said, "You can't do that." Now, I had talked on the phone to Horowitz a little while before and explained to him why you could, whereupon he started giving my lecture to Hennessy, and I was able to sit down. It was wonderful. What's really outrageous is what the register file can do. One of the things the register file can do is anytime it feels like informing the rest of the pipe of a value of a register, it can simply drop it into the results pipe. And if that value happens to be the most current one, it will go down and somebody will garner, some other instruction will garner something from it. If that value happens to be obsolete, the instruction that obsoletes it is somewhere in the pipe and will kill it before it gets and does any damage. And so this is a very permissive design. It says the register file may do that. Now, maybe it's not a good thing to do, but it's not harmful. And so one way to make a spiral pipeline actually functional is simply to periodically go through the register file and drop all the values into the results file. And that guarantees you that you'll avoid deadlock, because if there's some instruction down there waiting for a particular register value, hey, eventually it'll come along. Now, that's clearly not very efficient. One could do a lot better. One could sort of predict which values are needed down there. I mean, I noticed that recently register 3 has been kind of popular. So I'll put register 3 in the results pipe more often than other registers, and that might help the efficiency a bit. What in fact we do is two things. We notice in the instruction decode which values are actually needed. And we provide hints to the register file. Some instruction has now come on board that needs values for register 3 and 8. How about putting them into the results pipe? And so the register file does that, and there's this advanced warning kind of special connection that tells the register file what to do. We actually do something more than that, which is down near the bottom of the pipeline somewhere, we put what we call as a register cache, which is not a complete copy of the register file, but just a few registers, say a handful. And these are the popular ones. They're the stack pointer. Okay? They're, a couple of other constants that people are using all the time. Whatever has been popular sits down at the bottom so that instructions can garner from that the values that they need. Now, it turns out that the semantics of a register cache are identical to the semantics of the results pipe itself. And it turns out that most of the results that instructions need were computed only 1 or 2 instructions earlier anyhow. And so one of the important functions of the register cache is to notice if any instruction has gone past, which will compute a value of register 5. I don't know what register 5 is, but somebody just went by who's going to compute it. Here's another instruction that needs a value for register 5. I haven't seen register 5 come back down the results pipe, so clearly it must be up there somewhere. Let's not bother the register file with this. We know it's already there, and the results pipe itself serves as the principal register cache. And what's remarkable about Sproul's design is how short a distance in the results pipe information actually flows. One of our principal concerns has been that providing only one path for information to get from earlier instructions to later instructions might not be enough. But it appears, at least from the measurements we've made so far, that one path is not very heavily used, in the sense that it's really many paths in different parts of the pipeline. And it is only needed for the portions of the path that go from where an instruction computes to where the next one needs its value. The statistics of real programs tell you that information is needed usually not very far from where it's computed. I'm happy to answer questions if I can see the people in the back. Wave your hand big, so go ahead.
Where do the results stay when it gets to the bottom?
They fall off the bottom.
If they're going to be used like a long time from now, but they aren't going to be used.
They might be cached. It would be nice if the programmer, if the compiler would tell us. I mean, if there were some hints in the code, it would be helpful. But you can do pretty well just by doing the obvious thing you do for a cache. At least most recently used is useful. Yeah.
But the primitive value of the register
Is it the register file?
percolating up and sticks in the
Right. The register file carries the permanent value. Yeah.
Did you think about a back door to get to the register file when you had a result, instead of just percolating it?
No, you want to percolate up because it's there to kill other results that might be wrong coming down. Let me talk about sightings. I see I've got about 15, 20 minutes. Kleinrock having given most of my lecture. Wait till you give an hour talk for me and see what introduction I give you.
It's called open.
Okay, now in this picture, those 3 dots mean that there may be many stages in between the stages I've actually illustrated. I don't know how long a Sproul pipeline processor should be. Maybe it should be, conventional wisdom says pipelines for microprocessors should be 6 or 8 stages long, not very long. Maybe a Sproul pipeline should be short like that. Maybe it should be 20 or so stages. At the moment, I'm voting for about 20 or so, but there are members of my group who say, 6 or 8, and the answer to that question is not yet known. Maybe Gordon Bell is right. There shouldn't be any stages at all.
Seems like,
I can't see you up there.
seems like there's two ideas that you've got pipeline and architecture, and you've got asynchronous.
Yes,
You can design the same thing synchronous.
you betcha. Absolutely.
About the same speed, or there's just
We haven't any idea. Feel free to take Sproul's architecture and make a synchronous design. The architecture doesn't care. The important thing about the architecture from our point of view is it's got very local communication. And so it is an architecture that's very suitable for the asynchronous form.
there seems to be so much, interaction, the way things have to communicate, that you might lose a lot of advantages of asynchronous.
Boy, that's the mystery, is will we? Okay, we spent a lot of time on that. I'll say a little bit about that in a minute. Let's talk about sidings. Supposing I have a multiply operation, for example, that may take considerable time, longer than it takes to move an instruction from one stage to another, I can make a pipeline multiplier of some kind, which might connect to the main pipeline in two places. When an instruction gets to the multiply launch stage, it waits until it's got the values, the operands that need to be multiplied, and then it launches the multiplication into the multiplier and moves on. When it gets to the multiply return stage, it waits until the multiplier gives it an answer, and then says, oh, it's as if I computed that myself. It drops the answer into the results pipe and carries the answer forward to the register file. Supposing I had two such pipes that were interlocked, two such sidings that were interlocked, like that, then I would have something which was highly suitable for doing dot product. Namely, I do a multiplication, the multiplication drops its answer into here where the other sum is waiting. The addition gets done, the sum drops back down, waiting for the addition launch, and so on. And so an interlocking structure of that kind could be highly efficient for dot product. The results don't have to move very far in order to get involved. Okay, now I'm going to skip some slides. Trust me, you've seen them. They're just the combinations that I just put up. If you don't believe me, there's... Okay, let me talk about memory. I'm going to wave my hands a little bit here, but not too much. We think of the memory function as a siding also. There's a memory launch stage, supposing that I'm doing some kind of load operation. In the memory launch stage, the load instruction waits until it has the address from which to load all the values it needs to tell the memory to do a load. Then there's two return paths, one fairly soon and one further up the pipe. So if the memory system finds the value that's been requested in its cache memory, it responds early to the load instruction and says, here's your value. So having launched the memory request, the load instruction is free to move forward to the cache return stage where it waits for an answer from the memory system. Unlike some memory systems, it's required that this memory system return an answer even if the answer is, I'm sorry, I don't know the value. If the instruction gets the I'm sorry signal, it says, okay, I got to move on, but I don't know the value yet. It moves up to the memory return stage where it waits until it really does get the value back. Now the purpose of this is to enable a quick return of memory information that may be available quickly and to permit slower return of information that may be available more slowly. Okay, I've talked quite a bit about this. Let me talk about the asynchrony part of it. I mentioned the arbitration problem. Let me just show you a little bit about the character of this funny pipeline in operation. Here is a picture which exhibits the flow of information through this pipeline. What you see vertically is a picture of the pipeline and horizontally is time. So think of this as an image, moving image where time progresses across like this. And red are instructions and blue are results. The data here, the program, is not a real program. The program here is just at the bottom of the pipe we're sticking in instructions and at the top of the pipe we're sticking in results. The gray areas are where garnering and renrag, those computation processes, are going on. And so you can see there's a characteristic advance rate of instructions which is about that angle when the pipe is empty. That represents an advance rate for the instruction and an advance rate for a result. When the instructions have to meet other results and do the comparison computations, they progress more slowly. And so the average slope is quite different. So here's when the result pipe is empty. Here's when there's information to be compared to. And you see this quite characteristic structure if you look just at the gray blocks. You see that the gray blocks look a little bit like a brick wall. And in fact, if I make the number of instructions per second and the number of results per second match, you'll notice that the gray blocks assume the geometry of bricks and brick wall. And that's characteristic of the behavior of this system, although it's asynchronous. What happens is instructions and results meet in all of the odd stages and do their comparison. And then everybody moves one stage. The instructions move one stage up, and the results move one stage down. Okay, and so now comparisons happen in the even stages. And then everybody moves one stage. The instructions move up, the results move down, and comparisons happen in the odd stage. And that's a characteristic cyclic behavior which this asynchronous system gets itself into because of the time delays and how all the time delays work out. Right. That's what it says here. But if we take this very same picture and extend it in time, this is the result of some rather simple simulations that were done last summer by one of our summer interns. And he noticed this pattern. Does everybody see blue mountains and red sky there? Okay? And there's sort of a white zigzag line. Well, there's a limit cycle which ends up here. This white zigzag line goes on for as long as we've cared to simulate. And you can ask me, what the hell is that? I haven't the slightest idea. But what's more important is I don't care. Because I know that locally, the arbitration is happening correctly so that the comparisons are being done properly. I know that information is flowing and is not being lost through the pipeline. And the details of the timing I really don't care about. All I care about is the average delays of what's going on. And I'm pretty sure that the systems that we build will have all kinds of little detailed phenomena of this sort. And it may be that if this is a successful project, people will begin to study those second-order phenomena and try and figure out what causes them and whether systems can be improved by tuning up delays in various ways. Well, one of the things that this simulation did was to say, this is an asynchronous system, so the specific values of delays shouldn't matter. I wonder what would happen if the delays of different operations vary just a little bit, let's say 1% or 2%, but at random. So if something's going to take, 100 nanoseconds, this time that we do it, let's simulate it with 101, and next time with 99, and now with 100, and now with 99, and so on. And so we did that with the simulator, and here's a resulting pattern. And it looks a little random. On the other hand, you can still see the kind of regularity of blue diagonals coming down and red diagonals going up, and a sort of brickwork of gray spaces in between, which are the characteristics of this kind of asynchronous pipeline. Now, I think I've come to the end of what I want to say, but I'd like to be a little philosophical for a moment about this particular project. We got started saying, let's see what we can do about making an asynchronous system. We had done some preliminary work with asynchronous FIFOs and a variety of other asynchronous structures, and it all seemed pretty simple. And we said, let's understand what that might mean at the system level, and we started working on Sproul's architecture. And then Charlie Molnar did the Molnar 5-state diagram, which is deceptively simple. But it embedded in there are some very great subtleties. Just what does that arbitration really mean? Just what do you really have to do to ensure that instructions can be resolved? And the subtlety of that led us to arbiters which are of a peculiar kind, which have a common done signal instead of separate done signals for the two processes that are being arbitrated. And that's led us in a variety of directions, which have been quite rich beyond what we ever expected when we started. And the way I like to put this is this project has proven to be a worthy intellectual autonomy. This is tough stuff. And the tough stuff is in the subtleties of just what is meant. Design of asynchronous systems appears to be hard, and I think it's fundamentally hard, and I think I could summarize the reason. If you have n wires in a synchronous system, there are only 2 to the n combinations to worry about. And what happens in reaching those 2 to the n combinations matters not. All that matters is what is the configuration of those wires when the clock goes tick. Where is everybody standing on the next beat of the drum? In what position were they when the flash photograph went off? That's all that matters. It doesn't matter how they got there. When you deal with an asynchronous system with n wires, there are n factorial orders in which they may change. And n factorial is far larger than 2 to the n. And it may be that that's the fundamental reason that asynchrony is hard to deal with. You have somehow to worry about all n factorial of those possibilities. And one way or another, you have to limit what the system can do to avoid those combinations that you do not wish to have, and preserve only those which will give you the behavior that you're designing for. Well, we've had to develop some notation, we've had to develop some CAD software, but most important, we've had to develop some intellectual understanding of what it is we're doing. And sad but true, most of our progress has been made by forgetting things that we thought were correct. I'll give you an example. We all know from synchronous system design that latching a latch is the important thing to do. By God, when the clock comes along, I latch that data and I've got it. Well, we use all one-level latches, which have the property that when you latch, the output does not change. And so latching a latch doesn't change the output, so it's a non-event. The important event is unlatching the latch, which causes the output to change. And so we have to forget everything we knew about latching the latch being important and realize that it's the unlatching that's important. And that's a very hard step to take, having been steeped ever since I was at MIT 30 years ago. You know, that latching is important, I've had to unlearn that. And now you graduate students, this is the enormous advantage you have over the faculty, is you haven't a clue as to how it's supposed to be done. And so you don't have anything to unlearn. And so you have the chance to do something new that those older guys would have a hell of a time thinking of, because it's not the way their heads work. And my experience in life has always been that unlearning the things that I knew, and I was sure were right, is so much harder than learning new stuff, that I wanted to share with you younger people that you have an enormous opportunity simply because of what you don't know. And keep that in mind as you talk to these old guys who are doing it wrong. That's the end of what I have.